In this video we're going to look at momentum. We need to know how to calculate momentum, we need to know how to work out the force required to make something change momentum, and then we're going to look at a law called the conservation of momentum, which is going to help us work out what would happen in a collision. Okay, this is a question to think about in the first place. Which of these two has the greater momentum? Another way to think about that, a nice way to think about it, would be who would it be harder to stop? You frequently get two answers to this one. Someone would say the dog, someone would say the woman. The people who say that the woman they think has the dog has more momentum is because he's travelling faster. And they're right, that's an important factor in momentum, how fast you're travelling. Other people might argue that as the woman is heavier, she would be harder to stop, so she must have more momentum. Ultimately, to gain momentum or to lose momentum, you need to apply a force. So whoever would be the hardest to stop, I think in this example, probably would be the woman. So she's probably got the greatest momentum. But we've got the two sides of the argument here. You need to have either speed or you need to have mass. Well, actually, you need a combination of the two, and the higher combination you have of the two, the more momentum that you will have. So, how is momentum calculated, first off? It's an equation and we can't really get around it. So momentum is equal to the mass times by the velocity, as we just discussed with those two cars. The things that were important were how fast they were travelling and how much mass they had. So if they've got mass and they're moving, then they will have momentum. If they've got mass and they're standing still, they will have no momentum. The units that we use here that are standard, mass is in kilograms and velocity we use meters per second. Subsequently, the unit that we get from putting those together is kilograms meters per second. So it's a bit of a mouthful as a unit, but it is important to make sure that you're comfortable in quoting momentums in these terms. Right, let's have a go at calculating momentum here. I want you to have a go at this question, and then when you've done that, I want you to then have a think about this. What would happen to the momentum if we were to increase the speed to 30 meters per second? So in the original example, we've got an aircraft carrier with a mass of 1,000,000 kilograms. And it's travelling at a velocity of 15 meters per second. So first off, what is its momentum? Second, what would happen to momentum if we increased its speed to 30 meters per second? Pause the video and have a go. Right, so we use the equation that we had before, which is that momentum is equal to mass times by velocity. The mass is 1,000,000 kilograms and the velocity is 15 meters per second. So that's already in the units we discussed before. Subsequently, all we need to do is times those two numbers by each other. And we get 1,000,000 times 15, which gives us 15,000,000 kilogram meters per second. As the units originally given to us were in kilograms and meters per second, it's not complicated. Now the second part to this question. What would happen to its momentum if its speed were to increase to 30 meters per second? Well, hopefully this will be intuitively obvious. The only two things that can affect the momentum are the mass and the velocity has gone up from 15 to 30, so it's doubled. The mass hasn't changed. If we double one of these numbers, we should see that the number will double. So let's work it out just to check. So momentum is equal to mass times by velocity. So its momentum equals 1,000,000 times by 30 meters per second. That gives us 30 million kilogram. Scrub that out, let's make sure we get this absolutely right. Kilogram meters per second. 30,000 kilogram meters per second, twice the number that was before. If we double the velocity of an object and don't increase its mass, its momentum doubles. If we kept it at the same speed and doubled its mass, its momentum would double. These are the only two things that can affect the momentum of an object. Right, now we're moving on nice and quickly to force and change in momentum. Calculating momentum is relatively simple. We now need to see how a force will cause a change in momentum. The change in momentum depends on the size of the force that you've applied and how long you apply it for. So the equation that we use to define this is that the force required to make a certain change in momentum is equal to the change in momentum. Not just the momentum, because it may have started with momentum, we don't know. So the change in momentum divided by the amount of time that the force was applied for. What that equally tells us is that the change in momentum is equal to the force that you apply times by the time that you apply it for. So the more time you apply a force for, the more you'll change its momentum. Or the more force you apply for a certain amount of time, the more change in momentum. Momentum is the same units as before, kilograms meters per second. Time is in seconds, and force we measure in newtons. Right, let's try and apply that equation. So the equation was force is equal to change in momentum divided by time. A rugby ball of mass 0.5 kilograms is kicked from stationary to a velocity of 8 meters per second. The kicker's foot is in contact with the ball for 0.1 seconds. What is the force? Pause the video and try and work this out. Okay, so we're going to use the equation that we just applied, and that's force is equal to change in momentum divided by time. And that is equal to force equals change in momentum divided by time. And that's equal to force equals change in momentum divided by time. We're going to work out change in momentum here, and then we'll apply that to get the total number. So to get a change in, you need to know what the momentum was before the change, before the force was applied. You need to know what the momentum was after the force was applied. So before, we've got a mass of 0. So we know that momentum, and the symbol for momentum is a p, equals the mass times by the velocity. So the mass, it was equal to 0.5 kilograms, and the velocity, well, it was stationary. That means that its velocity was 0. Which means our momentum before is actually quite simple. It was equal to 0.5 times 0. Afterwards, it was still having a mass of 0.5 kilograms, but it was travelling at 8 meters per second. That means that it had a momentum of 4 meters, and again, kilogram meters per second. So, all we need to do to get the change in momentum is that we take away the before from the after. So we'd do 0.5 times by 8 minus 0.5 times by 0. And then the amount of time that it took was, just to extract it from the question, 0.1 seconds. So 0.5 times by 8 minus 0.5 times 0, that gives us the change in momentum. This was before. Oh, no, it wasn't. This was afterwards. And this one was the momentum before. So after minus before gives you the change in momentum. It changed in momentum by 4 kilogram meters per second, and it took 0.1 seconds. So you divide 4 by 0.1, you get 40 newtons was the force that needed to be applied to change the momentum of that ball by that amount. Right, so now we have managed to calculate the force needed to make something change momentum in a certain amount of time. We've worked out momentum itself for an object, and we're whistling through now, which means we're on to the third thing here, which is conservation of momentum. Being able to work out momentum is really important for this. The whole reason really that we focus on momentum is because it is conserved. This means that we can actually predict a lot about the way that things will behave, because we know that this is absolutely true, and we've never been able to break this not being the case. The conservation of something is quite simple. When we say that something's conserved, we mean that we can't lose an amount of it. So, the total momentum before a collision occurs is equal to the total momentum after a collision occurs. This one fact, is really useful for us, and it can allow us to predict the behaviour of lots of different scenarios. So it's very important that we are able to calculate it. Right, with this equation in mind, let's go forwards and try and do some calculations. First off, I'm going to go through a convention as to how I like to draw objects that are colliding in a nice, sensible way. Okay, so how do we draw diagrams of these collisions, and how do we make sure that what's happening is really clear? I like to draw everything as a ball. So if I was going to draw two spheres, for example, that were going to collide, I'm going to look at what they're doing before and what they do afterwards. So I've got sphere 1 and sphere 2. initially they are travelling towards each other, and we're going to use the convention here where u is the initial speed and v is the final speed. So u1 is the initial speed of object 1 and v1 is the final speed of object 1. Same for object 2, u2, v2. And its mass is m1 and its mass of object 2 is m2. So can you work out what the momentum before, in terms of these symbols, is? Can you work out what the momentum afterwards is? Pause the video, have a go. Right, so momentum is equal to mass times by the velocity. This is the mass of object 1, this is the velocity of object 1. So the momentum of object 1 would be m1 times by u1. And the momentum of object 2 would be m2 times by u2. We don't need to consider the fact that this is an opposite direction yet. When we put a number in, we would have to consider which direction we consider to be positive. So the momentum before is equal to m1 u1 plus m2 u2. The momentum afterwards, we've still got the same masses, and momentum still calculated in the same way, but instead of u's we've got v's. So the momentum afterwards is equal to m1 v1 plus m2 v2. When we look at the direction things are travelling, we will have to consider a positive or negative number when we start to look at real examples. Let's look at an example now. We have our object 1, this time we know its mass, we know that it's 6 kilograms, and it's going to travel at this object 2 with a velocity of 3 meters per second. The other object is travelling towards it with a speed of 4 meters per second, and its mass is 4 kilograms. We know the masses of both in before and afterwards, they don't change. And afterwards, this sphere moves off in the opposite direction with a speed of 1 meter per second. What I want you to be able to try and calculate here, using the conservation of momentum, using the fact that the momentum before is equal to the momentum afterwards, I want you to try and find out what speed, what velocity the second sphere moves off with. So what is this? Pause the video and have a go. Right, let's work this out. So let's find the total momentum before. So the momentum of sphere 1 is equal to, so we know that momentum is equal to mass times velocity, so it's equal to the mass, 6 kilograms, times by 3 meters per second, and that gives us 18 kilogram meters per second. The momentum of this object we calculate by timesing its mass by its velocity, but at this point we need to start considering which direction we're going to consider positive. So let's say that we've only got things travelling left and right, but let's pick directions anyway. I'm going to say that anything travelling right has a positive number, and anything travelling up would also have a positive number. This is my standard convention for this sort of thing. Anything travelling down, therefore, or anything travelling left, would have a negative number attached to it. So we've often got the size. So if it's travelling left, that means its number is negative. If it's travelling down, its number is negative. Up and to the right, positive. So I've already followed this convention in this one here. I chose the 3 meters per second as being a positive number. I should really have defined this before I started. So I have my mass of 4 kilograms, and I'm going to times that by the velocity. The scalar is 4 meters per second, but it's travelling left, which means I have to choose a negative number, so times by minus 4. So the total before is equal to 18 plus minus 16, 4 times minus 4. That gives me a total momentum of 2 kilogram meters per second. Now what's the momentum afterwards? We have a sphere of 6 kilograms travelling at 1 meter per second, but it's to the left. As it's to the left, that is times by minus 1 meter per second. That gives me minus 6 kilogram meters per second. And then I need to add the momentum of the second sphere. So 4 kilograms times by this velocity that we don't know yet, v2. So I know that minus 6 plus 4 times by v2 is equal to the momentum afterwards. Now, do we know the momentum afterwards? Well, yes, we do. This here was the momentum before. The conservation of momentum tells me that the total momentum before is equal to the total momentum afterwards. So this is equal to 2 kilogram meters per second. All I need to do now is rearrange this equation. So I've got minus 6 plus 4 equals 2. So I'm going to move the minus 6 over to the other side by adding 6. So I've got 4 v2 is equal to 8. v2 then is equal to 8 divided by 4, which is 2 meters per second. This number has come out positive, which means, just as was drawn in this diagram, it's travelling to the right. Okay, we've got a few special cases that we need to look at. One of them is something called an explosion. That sounds more dramatic than many explosions that might be given as examples. An explosion is when two objects start together as one object almost, and then they split apart. So this could be trapeze artists holding each other together at the centre of a trapeze, or it could be a person on a boat and stepping off of it, or it could actually be something exploding, two particles moving out from a central point. So before, with this example, they don't tend to be moving. Their initial velocities are 0. As such, to conserve momentum, the momentum of this object moving in that direction has to cancel out the momentum of the other object moving in the other direction. If they've got the same mass, that means that in any explosion, the two objects will move off with the same velocity. So they'll move off with v1 and v2, and the v will be dependent on the mass. The more mass it's got, the slower it will move away, because these need to have equal size momentum, but they'll be in opposite directions. So one will be positive and one will be negative, cancelling each other out and coming back to 0. A second example that we've got is things coalescing or sticking together. So if we fired these two at each other, and a bit like often happens in car crashes, instead of them bouncing off of each other, they get jarred together, they become one object and move off together. So if they move in towards each other and they coalesce or stick together, they're going to move together as one mass. So in essence the mass has changed, but we don't have two masses anymore. As such, we have a slightly different term. Instead of m1v1 plus m2v2, we've got m1 plus m2 times by a common v. They're not moving at different velocities, they're moving away together. So we end up with their momentum being m1 plus m2 times by their velocity together. They're moving at a single speed. The two of them are just moving at this one velocity v. So we add their two masses together and times it by v. And that will have to equal the same thing as we had before here. Okay, a few questions. I want you to think about these. I'm going to get you to pause it in a second, then we will talk through each of the answers. What is the total momentum of these two trapeze artists who are not moving? When they let go, what will happen to them? As they've increased in speed, is momentum conserved? Why? Okay, pause the video, have a think. Right, let's go through these questions one by one. What is the total momentum of these two trapeze artists? Well, this is a photo, but we can assume that they're not moving. As momentum is equal to mass times by velocity, and velocity in this example is 0 meters per second, their momentum must equal 0. So their total momentum is equal to 0. They're not moving. Now what will happen when they let go? This man is going to go that way, and this man is going to go that way. And they're going to start moving. So they will both start to move. Which means their momentum will increase. Individually, his momentum will increase and his momentum will increase. So they've increased in speed. We've said that there was no momentum before, whereas clearly they're moving now, so they do have momentum. Why is it conserved? Well, the really important thing here is that this man is moving this way, and this man is moving in this direction. As we said before, with any vector, we have to pick positive and negative directions. So if I choose to the right as being positive, that means any movement to the left would be negative. So, although this man increases in momentum in this positive direction, because we know that the conservation of momentum is true, this man will increase in momentum in the opposite direction by the same amount. And they're going to reach a number that cancels each other's momentum out. They'd have to. So we know that the mass of this man times by his velocity is going to have to equal the size of the mass times by the velocity of this man. But because this is going to be a negative velocity here, this will cancel out this momentum. Okay, let's have a go at this question. You can see here an explosion, a really clear and evident explosion. We have initially a shell inside of this gun here, and it is not moving at the start. An explosion occurs and a shell shoots off that way and the gun moves backwards. So they're moving in opposite directions. That's a good sign initially for that momentum is being conserved. We have a shell of mass 48 kilograms and a gun far more massive, 3,420 kilograms. The gun has moved backwards there about 3 meters in 1 second. It's moving at a velocity of 3 meters per second. In this question, I want you to try and work out what velocity must the shell move in this direction, off that way, if momentum is going to be conserved. We've already got an object increasing in its momentum in this direction, and we know its mass. And we know its velocity. What velocity must this shell move in this direction to cancel that momentum out? Pause the video and have a go. Right, let's have a go at this question. Mass is equal to 48 kilograms for the shell, 3,420 kilograms for the gun. We know that the gun moves backwards with a velocity of 3 meters per second afterwards. Okay, so let's simplify this slightly in a diagram, just as I demonstrated before. So we've got mass 1 and we've got mass 2. This is an explosion, they're starting together. And they have U2 and they have U1. U1 and U2 are equal to 0. We know that, let's say that M1, this is our shell, and this is the gun. So we know that M1 is equal to 48 kilograms, and we know that M2 is equal to 3,420. So with any of these problems, I'd like to do a before and after split. Work out what the before is, and we know that that's equal to the momentum afterwards. So before, momentum of the shell is equal to M1 U1. So momentum, I'm going to call that P shell, is equal to M1 U1, which is equal to 48 times by 0, which is equal to 0. And the momentum of the gun is equal to M2 U2, which is equal to 3,420 times by 0, which again is equal to 0. So total before is equal to 0 plus 0, 0. So the total momentum before we start is 0 kilogram meters per second. Let's have a look at the after case. We have our shell and our gun moving away with different velocities. So this was M1, our shell, moving away, we're assuming with quite a high velocity, V1. And we have our gun moving away with a lower velocity of 3 meters per second. And we know it's got mass M2 is equal to 3,420 kilograms. This one was 48. So, total momentum afterwards is going to equal V1 times by M1. We don't know V1 yet. We can add that, we need to add the momentum of these two objects together, so we can add that to M2, which is 3420, times by 3. Right, now we need to equate this to what we found out before. So we know that this plus this, we've got an unknown here that we need to try and work out, is equal to 0. Now there's one mistake I've made here, spot the mistake. I haven't chosen a positive or a negative direction. Let's say that this direction, just as before, is positive. As such, actually I don't need to change any of these numbers. This is a positive number that I've entered into here, and V1 should hopefully come out therefore as negative because it should be travelling in the opposite direction. Let's see if that happens. So we've got an equation set up here. The momentum afterwards is equal to this plus this, and we know that momentum must equal 0 because the total momentum before was equal to 0. So let's keep V1 times by 48 over here, and that's going to equal minus 10,260, which is just 3,420 times by 3. We then need to divide by 48 to get V1, so V1 is equal to minus 10,260 divided by 48, and that comes out as minus 213.8 meters per second. So there we go, we've got the crucial negative here, which because of this sign convention that we picked, where I put this in as positive, this in as positive, the 3 is positive to the right, it's come out as minus 213.8 meters per second, which means it's travelling left, it's travelling in the opposite direction. 213.8 times by 48 is equal to 10,260. So we know that the momentum of this is equal to the momentum of that, but in the opposite direction, so they're equal in magnitude, but they're not the same. So the total momentum afterwards is equal to 0, same as before, and we've worked out the speed that this shell would move away with. This example is quite involved and quite difficult. If you followed that, then that's absolutely fantastic. If not, feel free to go back and have a look at some of the simpler examples that we've used. Okay, I want you to have a go at these questions. They are attached to the video in a PowerPoint, or you can just pause the video and have a go at them now.